Arithmetic sequences as functions. A sequence in mathematics is a collection of numbers, symbols, or objects that are ordered and follow a particular pattern. Individual values of a sequence are called terms and are identified by the position in the sequence. An arithmetic sequence is a sequence of numbers with a common difference that can be written in this form right here, where A1 is the first term of the sequence and D is the common difference. So A1 is the first term of the sequence. The second term of the sequence is going to be the first term plus whatever the common difference is. The next term, the third term, is going to be that first term plus twice the common difference. And then number 4, the fourth term in the sequence, is going to be the first term plus 3 times the common difference. And that keeps repeating for infinity. Example number 1. Given two sequences, 5, 7, 9, 11, and the second sequence is 23, 17, 11, and so on. The 3 dots mean that these sequences continue forever. The value of A sub 1 and D are found by listing the first term and then adding the common difference between the terms. So we have here 5 is the first term. Now the common difference is 2. If you take a look, you take any term and subtract the previous term, you'll get the common difference. 11 minus 9 is 2, 9 minus 7 is 2, 7 minus 5 is 2. So that's the common difference. So notice that 7 is the first term, 5, plus 2. If we add another 2, that takes us to 9, or it's the first term, 5, plus 2 times the common difference. The next term is 11. Okay? We get that by adding 2 to 9, or we can take the first term, 5, and add 3 times the common difference. So A1 is 5, the common difference is 2. Now, for the other example where we have 23, 17, and 11, okay, that is found, we take the common difference, you take the previous term, you take a term and subtract the previous term. So 11 minus 17 is negative 6. 17 minus 23 is negative 6. So the common difference is negative 6. The first term is 23. So notice we start with 23. We add a negative 6, which gives us 17. The next term is 11. That's found by taking the first term, 23, and adding twice the common difference, 2 times negative 6, which will give you 11. The next term, if we wanted to find that, would be 23 plus 3 times negative 6, which is 5. Let's talk about explicit formulas. An explicit formula directly calculates any term in a sequence using its position without needing previous terms. Linear sequences can be represented with an explicit formula that enables you to find the terms of the sequence. Here is the general explicit formula. A sub n is equal to A sub 1 plus the quantity n minus 1 times d, where n is the term number in the sequence and d is the common difference between the terms. Explicit formula example number 1. Given the explicit formula, A sub n is equal to 6 plus n minus 1 times 3. The sequence is written in list form by finding A1 and D by matching them with the formula. So here we have our general explicit formula. Notice the A1, in this case, is 6, and D is 3. So when we make our substitution, okay, we're going to start by substituting n with 1. So here's where I substitute n with 1 here and here. We verify that A1 is 6, just like we said, A1 is 6, and the common difference is 3. So we have the same formula that we started with. Now, we're going to substitute n and d into the explicit formula to find other terms. So first time we substitute n is equal to 2. So here and here we replace n with 2. And the second term in the sequence is 9. Next we're going to replace n with 3. here and here. And the third term of the sequence is going to be 12. Next, let's replace n with 4, here and here. And the fourth term of the sequence is going to be 15. And finally, we're going to replace n with 5, here and here. And doing the arithmetic, we find that the fifth term is 18. And that's what we're saying here. The sequence of a sub n is 6, 9, 12, 15, 18, and so on. And we can continue this to infinity. Now let's talk about the recursive formula. Linear sequences can also be represented with a recursive formula that enables you to find the terms of the sequence. Note what the recursive formula looks like. It's a sub n is equal to a sub n minus 1 plus d, with a starting value of a sub 1, where a sub n depends on the value of the previous term, and d is the common difference. So what is a recursive formula? A recursive formula allows you to find the next term in the sequence. So given a particular term, you can use this recursive formula to find the next term in the sequence. Note the difference between this formula and the explicit formula, and the purpose of the two. The recursive formula allows you to find the next term, while the explicit formula allows you to find any term in the sequence. This example will explain how the recursive formula works. Given the recursive formula, a sub n is equal to a sub n minus 1 plus d, with a starting value of a sub 1 is equal to 4, the sequence is written in list form by assigning n is equal to 1 and a sub 1 is equal to 4. And observing that d is equal to 3 for this sequence, we get a specific formula that a sub n is equal to a sub n minus 1 plus 3. And we're also assigned that the first term is equal to 4. So I want you to think of this. A sub n would be the next term, and a sub n minus 1 is the previous term. So think of it that way. So this is the next term is found by taking the previous term and adding the common difference, which in this case is 3. So let's take a look and see how this formula works and how do we apply it. And our goal is to calculate the values for a sub n for the second term, the third term, and the fourth term. And we do that by adding 3 to the previous term. So a sub n minus 1 is a way to write the previous term. Step 1. When n is equal to 1, a sub 1 is equal to 4. That's the first term of the sequence. So to find the second term, we now move n up to 2. So n is now equal to 2. Notice the next term is a sub 2. That's the second term. And see this n minus 1 right here? Well, 2 minus 1 is 1. So that's a sub 1. But what's a sub 1? It's 4. So I take 4 plus 3, and that gives us the second term. A sub 2 is equal to 7. Okay, let's go to step number 3. Now n is equal to 3. So our third term is going to be the previous term plus 3. So again, n minus 1 would be 3 minus 1 is 2. So what's a sub 2? A sub 2 is 7. So I replace a sub 2 with 7, and I add 3 to get my third term is 10. So my third term is 10. Now let's make n equal 4 for the fourth term. So we have a sub 4 is equal to the third term, the previous term. Okay, remember 4 minus 1 is 3. That's why we have this little n minus 1 subscript here. So my fourth term is equal to the third term plus 3. What's the third term? The third term is 10. So the fourth term is going to be 13. And that's how we generate the first 4 terms of the sequence. The first term is 4, the second term is 7, the third term is 10, and the fourth term is 13. If I want to calculate the fifth term, I would have a sub 5 for the fifth term is equal to the fourth term, a sub 4 plus 3. Well, a sub 4 is 13. And 13 plus 3 is 16. So the next term right here would be 16. And we can continue doing this forever. Explicit and recursive formula practice number 1. Write the sequence for this formula, where a sub n is equal to 12 minus 6 times n minus 1. So this actually is the explicit formula, which is used to find any term in a sequence without knowing the previous term. But to give you some context to practice here, let's say n is equal to, let's find the first 5 terms. So n is equal to 1, then n will equal 2, n is equal to 3, then 4, then 5. So we're just going to find the first 5 terms. So you'll practice using this formula 5 times. So we're going to use it like a recursive formula, even though it's an explicit formula. So pause the video, find the first 5 terms, and then resume watching the video when you figured it out. And welcome back. Let's see how you did. Before I explain what's going on here, I want to take a moment and demonstrate the power of the explicit formula. The explicit formula allows you to find any term in the sequence without knowing the previous term. So if I want to find, let me pick a number at random here. Let's say n is equal to 82. So I want to find the 82nd term in the sequence. So I replace n with 82. And this is going to be 12 minus 6 times 82 minus 1. And continuing the arithmetic, 12 minus 6 times 81, because 82 minus 1 is 81, is going to give me negative 474. So the 82nd term in the sequence is negative 474. I was able to calculate that without knowing the previous term. So the explicit formula gives you any term in a sequence. The recursive formula depends on the previous term. Now we are going to use this like a recursive formula because we are going to do 5 successive terms in a row. So when n is equal to 1, we find out that the first term is equal to 12. And we state that the common difference is negative 6. I'm going to come back to that. So let's find the second term. Okay, I've replaced n with 2 here and here. And completing the arithmetic, we find that the second term is 6. Now we're going to replace n with 3. So we have replaced n with 3 here and here. Completing the arithmetic, we have the third term is 0. Next, we replace n with 4. So I replace n here and here with 4. And completing the arithmetic, we have the fourth term is equal to negative 6. And finally, the fifth term, I replace n with 5 here and here. And completing the arithmetic, we see that the fifth term is negative 12. So the first 5 terms of the sequence are 12, 6, 0, negative 6, and negative 12. As bonus information, this is the common difference. I can use the common difference by subtracting 6 each time. So 12 minus 6 gives me 6. 6 minus 6 gives me 0. 0 minus 6 gives me negative 6. Negative 6 minus 6 gives me a negative 12. And I can continue subtracting 6 each time to figure out what the next term is. So there's another version or the application of the recursive formula. Explicit and recursive formula practice number 2. Write the sequence for this formula. A sub n is equal to 41 minus 4 times n minus 1. Now this is an explicit formula, but we're going to practice this by finding the first 5 terms of a sequence. So let n equal 1, and then let n equal 2, let n equal 3, then 4, then 5, and find the first 5 terms of the sequence. Pause the video, do that now, and when you've written the first 5 terms of the sequence, resume watching the video. And welcome back. Let's see how you did. So when n is equal to 1, completing the arithmetic, we make the substitution where n is equal to 1 here and here, and we find that the first term is equal to 41. Next, we're going to let n equal 2. So we replace n here with 2, and also again here. And completing the arithmetic, we find that the second term is 37. Then we replace n with 3, both here and here, and we find that the third term is equal to 33. Next, we're going to replace n with 4, here and here. Completing the arithmetic, we find out that the fourth term is 29. And finally, when n is equal to 5, we replace n with 5 here and here. Completing the arithmetic, we find that the fifth term is equal to 25. So the first 5 terms of the sequence are 41, 37, 33, 29, and 25. And I want to make mention here of the common difference. The common difference can be used by subtracting 4 each time. So if I take 41 minus 4, that's going to give me 37. 37 minus 4 gives me 33. 33 minus 4 gives me 29. And 29 minus 4 gives me 25. So we can take advantage of the common difference once we know the first term. One other thing I want to do. Let's talk about the power of this being an explicit formula. I can use this explicit formula in a special way because I don't need to know the previous term. I can find each term in isolation. So let's say I want to find, let's pick a random number, 101. So I want to know if I were to carry this out to the 101st term, what number would that be? So I replace n with 101, and that's going to give me 41 minus 4 times 101 minus 1. And carrying out the arithmetic, we have 41 minus 4 times 100, which is going to equal negative 359. So the 101st term is going to be negative 359. So that illustrates that the explicit formula can be used to find any term without knowing what the previous term is. The recursive formula does rely on the previous term. Practice number 3. Write this sequence in a table, including its first 4 terms. And this actually is a recursive formula, so this time we're looking at a recursive formula. Notice the difference between a recursive formula and an explicit formula. Here we have the next term is dependent on the previous term plus 5. We're telling you that the common difference is 5, which means 5 is being added each time. And we're also telling you that the first term is 11. So pause the video, find the first 4 terms, and then resume watching the video when you have your answer. And welcome back. Let's see how you did. So we're going to run through this 4 times, starting with n is equal to 1 and our given value that the first term is 11, okay? So when we go to find our second term, okay, so a is our second term, it's the previous term, which is 11 plus 5, gives us 16. So now the second term is 16. Now we're going to find the third term. Okay, so n is now 3. So a sub 3 is equal to the second term, which is 16. 16 plus 5 is 21. So now to find the fourth term, we take, it's our fourth term, which is our third term, which is 21 plus 5, gives us our fourth term is 26. So in table form, when n is equal to 1, 2, 3, and 4, the terms are going to be the first term is 11, the second term is 16, the third term is 21, and the fourth term is 26. Practice number 4. Write the sequence in a table, including its first 5 terms. Now this is a recursive formula. Note the difference between a recursive formula and explicit formula. A recursive formula, you can calculate the next term by taking the previous term and adding a common difference. Here we're specifying that the common difference is 8. We also tell you the first term in the sequence is negative 10. There's 2 specific requirements. You want to write the sequence in a table, and you want to find the first 5 terms. So pause the video, find the first 5 terms of the sequence using this recursive formula, and when you have the answers, resume watching the video to compare your answers. And welcome back. Let's see how you did. So let's start with the table first, and I'll work backwards. So we see here that the first term is negative 10, the second term is negative 2, the third term is 6, the fourth term is 14, and the fifth term is 22. How did we calculate that? Well, we are starting with the first term is negative 10, and we're going to add 8 to each subsequent term to find the next value of a sub n, or a sub next. So the second term is going to be the first term, which is negative 10 plus 8 gives us negative 2. That's how we got the second term is negative 2. To find the third term, we take the second term and add 8. Well, remember the second term is negative 2, so negative 2 plus 8 is positive 6. So the third term is positive 6. To find the fourth term, we take the third term plus 8. The third term was 6, so we add 8 to get 14. So the fourth term is 14. And then finally, for the fifth term, we take the fourth term, which was 14, add 8, and we get 22. So you'll notice each time we're adding 8. Negative 10 plus 8 is negative 2. Negative 2 plus 8 is 16. 6, I'm sorry. 6 plus 8 is 14. That's what I was thinking of. And then 14 plus 8 is 22. Practice number 5. Determine if the sequence is arithmetic. If so, write a rule for the sequence in explicit form. So there's actually two things we're going to do. You have to make a determination. Is this an arithmetic sequence or not? If it is, write the rule in explicit form. Here are the three sequences. The first one is 9, 16, 23, and 30. And that continues on to infinity. Next, we have 1, 3, 6, 8, and 11. That continues on to infinity. And then we have 68, 57, 46, and 35. And that continues on to infinity. So pause the video. Determine if this sequence is an arithmetic sequence or not. And then, if it is, write the rule in explicit form. And welcome back. Let's compare answers. So to determine if a sequence falls under the category of an arithmetic sequence, there has to be the existence of a common difference. The same number that is the difference between any two terms. And this does exist. If we take any two terms and subtract its previous term, we're going to get the same number. So 30 minus 23 equals 7. If I take 23 and subtract that previous term, 23 minus 16 is also 7. And if I take 16 and subtract the previous term, that's going to be 16 minus 9 is also 7. And the fact that we keep getting the same answer proves that the existence of a common difference. That's how you know you have an arithmetic sequence. Now, as far as writing the rule in explicit form, we have to take a sub n is equal to the first term plus that common difference times n minus 1. Well, the common difference is 7, and the first term is 9. So that's why we have a sub n is equal to 9 plus 7 times n minus 1. Letter B, it's not an arithmetic sequence since the interval between each term is not the same. If I take 11 and subtract 8, that's going to give me 3. If I take 8 and subtract 6, that gives me 2. You have two different numbers here, and once you get two different numbers, you do not have an arithmetic sequence. You have a sequence, just not an arithmetic sequence. So not having a common difference disqualifies this from being an arithmetic sequence. Let's take a look at C. C, I'm going to take the two terms. I'm going to take 35 and subtract 46, and that gives us a negative 11. If I take 46 and subtract the previous term, which is 57, that also gives us a negative 11. And if I take 57 and subtract 68, I did that backwards. Hold on. The result is going to be negative 11. And the fact we get negative 11 all three times indicates that there is a common difference, negative 11. So we take our general formula, and we put the negative 11 right here in front of the n minus 1, and we take our first term and we put that right here. So a sub n is equal to 68 minus 11 times n minus 1. And that's how you determine whether or not a sequence is an arithmetic sequence and how you write the rule in explicit form.